Welcome back to Material and Energy Balances. In the last video, I showed you how to perform a reactive balance on a batch reactor. And because a batch reactor has no input or output, by its very nature, a batch reaction is an unsteady state situation. In this video, I'm going to extend those reactive material balances to a continuous reactor. But instead of at steady state operation, which is what we've been analyzing for the entire semester, I'll show you how to analyze and apply these balances during the transient startup period of this continuous reactor. So the piece of equipment here is called a CSTR, and that is an acronym that stands for Continuously Stirred Tank Reactor. The CSTR is a main piece of chemical engineering reaction equipment. It's one of several different types of reactors that, again, you will study in your future kinetics course. The continuously stirred part is an important part, and what this means is that we can apply the well-mixed assumption. So remember I said that the well-mixed assumption means that the concentration or the composition of the outlet stream is going to be equal to the composition inside the reactor at any time t. So we've seen this assumption before, and now the only difference is now this will be happening inside of a reactor, so we'll have a reaction to account for as well. So again, the best way to learn about this is to just look at an example problem. So let's take an elementary irreversible isomerization reaction, A goes to B, occurring in a 10-liter CSTR with a rate constant of 0.005 inverse seconds. We'll say the tank is initially full and the initial concentration of component A is 2 moles per liter, and it contains reactant A only. So the initial concentration of B is going to be assumed to be 0. At T is equal to 0, an inlet stream begins flowing into the CSTR at a flow rate of 1.15 liters per second and a concentration of 10 liters per second. An outlet stream is going to be exiting at the same volumetric flow rate. Obtain an expression for CA of T. All right, so let's draw a picture. Going to draw my picture in red. My CSTR has an inlet stream and an outlet stream, and it is stirred to be well mixed. I'm not going to label the mass or mole flow rate. I should be labeling the molar flow rate here. I'm going to label what I know, and I know what Vn is. I know that Vn is 1.15 liters per second, and my initial concentration, sorry, not my initial concentration. I have to be very careful with my notation here. So I'm going to have Ca0. I'm going to call that my concentration of the inlet stream. 10 moles per liter. Got to make sure that I keep my units organized as well. Now, Ca0 is going to be distinct from Ca of 0. So this is something that I see students mix up all the time. The difference between Ca of 0 and Ca naught. This Ca of 0 is an initial condition. Now, they both have the same units, by the way, moles per liter. This Ca naught is the inlet concentration. So you can use the notation, whatever notation you want, just make sure that it's consistent. I would strongly recommend sticking to my notation. It helps you keep things organized in that way. And because I have a well-mixed assumption here, I'm going to have Ca of T inside. That is going to be equal to Ca of T, the concentration of the outlet. My volumetric flow rate out is going to be equal to 1.15 liters per second, same as my volumetric flow rate in. So I can do the same trick that I did before of say that the volumetric flow rate in is equal to my volumetric flow rate out, and therefore my V is constant. So again, you can prove this with math if you like, or now that I've shown you that this is the case, if you can just look at it and say that V in is V out, that's going to mean that my volume is going to be constant. That, I think, is good enough. So to obtain an expression for Ca of T, let's go through the steps and first do my balance on component A. Component A balance, and that is of the form, general balance equation is in plus gen minus out minus consumption is equal to accumulation. And the only term that is going to cancel is going to be generation for component A. I'm not generating any component A because I have an irreversible reaction. So let's write it. I haven't written molar flow rates, but recognize that if I multiply V dot in times CA naught, I'm going to have liters canceling out. That's going to be moles per second. So my molar flow rate in is going to be CA0 times V dot in. Again, looking at my units, moles per liter times liters per second cancel out to give me moles per second. In a mole balance on component A, I should have each term giving me moles per second. So that's good. That's what I want. My outlet flow rate is going to be the concentration of the outlet stream, CA times V dot out. My consumption, it says up above that I have an elementary rate law. So elementary again means that I have the concentrations of the reactants proportional to, so it's K times CA. And then I messed this up last time. I'd like to just reiterate that the rate of a chemical reaction has to be an intensive quantity. It cannot depend on the size of the reaction. So K times CA is going to have units of moles per liter per, I'm sorry, moles per volume. Liter is a volume, right? So in order to, oh, I'm sorry, moles per volume per second. There's a time here too. Moles per time per second. And in order to get that into moles per time, I need to multiply by the reactor volume V. So the volumes here are going to cancel, or the liters are going to cancel in the units that I've written here. So once again, K is 1 per second. CA is moles per liter, just to be proper, and volume is going to be in liters. So I'm going to have the liters canceling, give me moles per second. The accumulation is going to be D times CA times V. So here, this CA is referring to the concentration inside the reactor. Inside reactor. And this CA, where am I going to draw my arrow? This CA is the concentration of the outlet stream. And because of the well-mixed assumption, they are the same value. I just want to be very clear about what each term means of outlet stream. I think that helps keep things very organized. I'll say that the whole class has been this way, that it's very easy to watch somebody else do a problem, but no topic is that more true for than unsteady state. So I really think that you have to do your own practice in doing these problems in order to get very good and proficient with them. All right, so this is my unsteady component A balance. And now I have a separable differential equation, believe it or not. All right, so I can say that the V is going to be constant, so I can pull it out of the integral, out of the derivative, and I can divide through by V. So I'm going to get CA0 times V in over V minus CA V out over V. And I can actually, instead of calling it V in and V out, I'm just going to call it V dot. And that way I can factor that out. So I'm going to factor out a V dot over V. So let's say up here, V in is equal to V out. And then this is equal to just V dot, we'll say. So V dot over V times CA0 minus CA minus KCA is equal to dCA dt. All right, separable differential equation. And actually looking at this now, I realize I should not have done that step because it's just going to make it a little bit trickier for me to integrate this. So I do have a separable differential equation now. And because I've got, it doesn't look like it, but I have 3 terms on this side, right? I would have 3 terms if I didn't factor out that V dot over V. So I need to take this entire thing over to the other side. So separating variables now, I'm going to get all my T's together, which is nothing. It's just a dt. And that is equal to, I need a big fraction here, 1 over all this stuff. So V dot over V times CA0 minus v dot over v. I'm going to group things differently. So it's v dot over v plus k times CA. All right, so I did that correctly, I think. So I have two minuses. I'm going to factor out the minus such that it's this plus this, dCA. I'm just going to double check. Yes, I think that is correct. On my left-hand side, I've got integral of dt is just t plus c, my constant of integration. This one looks like a tricky integral, but since v dot v, ca naught, and k are all constants, I can treat it just like an integral that I know how to take. So take 1 over 10 minus 5x, for instance. I know that the integral of this would be 1 over 5, so that's the inside derivative, times ln of 10 minus 5x. So it's just going to be the same form. So it's going to be minus out front, minus 1 over v dot over v plus k times ln of all this stuff. V dot over v, CA0 minus v dot over v plus k. I need the parentheses there, times CA. Okay, now I have to solve for CA. Okay, and I have to apologize because I know that I just skipped way ahead, but I was very apprehensive about making a mistake and I didn't want to have to go back and correct it. So I just decided to go slow, go at my own pace and work out this problem. I highly encourage you now to pause the video. First of all, pause the video. Don't look at what I've done yet, but try and work out the algebra from what I had done so far and see if you can get to this final step. This problem was actually pretty algebra intensive, and I do want to share that it would have been much easier had you plugged in numbers at the very beginning. I was very stubborn, and I didn't want to plug in numbers until the very end because I wanted to illustrate how it's very useful. Again, as engineers, we want to be able to solve multiple problems, or if the values change, we want to be able to not have to redo the problem. So doing it this way, working it out in variable names instead of numbers allows me to do that. Now, for any value of v dot v or k or ca naught or whatever, I can still use this same expression for ca as a function of time. I'm pretty sure this is correct. I have verified this with Excel. So a good way to double check your results. I'll go through a couple of ways to double check, but I'll just note that double checking methods that I like are simply, what I did is I went into Excel and I plotted this. So plot CA of t and double check that it makes sense with what you would expect. So I know that CA is going to start at time 0. Well, let me finish my thought. So plotting this in Excel to see the curve shape. And verifying and make sure that it makes sense. Okay, another way that you can double check this is you could try to take the derivative of this, right? So if you take the derivative of dCA of t with respect to t, we know what the derivative should be. So if you go back now and try to take the derivative of my function, I should get this back. Right? I don't think I want to do this on the video just for the purposes, I don't want it to be too long, but you should try this on your own. Try to take the derivative of this function and see that it goes back and cancels to what we had in the first place. Something else that I can do is plug in my initial condition and double check that it is the same value that you thought. So remember, my initial condition was at time equals 0. My concentration is 2, which I did up here in red. So I plugged that in order to find what the value of my constant C was. Well, if I plug in 0 for time there, that is going to kill the exponential term. Exponential of 0 is 1, and I'll be left with just 2 minus this term, and then this term is going to cancel out. So I'm going to be left with something plus 2 minus that same something is going to be equal to. Right, so plugging in my initial condition indeed works out. Another thing I can do to double check my answer is to check the steady state solution or the steady state value. So I know that because I'm starting up this CSTR, of interest to me is what is CA for time going to infinity? Because I know that eventually that CSTR is going to achieve some level of steady state. And maybe I'm interested in knowing what that value is. That's another analysis that you can do here. So there's two ways that you can double check what the steady state value is. And if they match, that's another indication that what you've done is correct. The first thing you can do is plug in t is equal to infinity. Well, mathematically correctly, t never equals infinity, but t tends towards infinity. When t tends towards infinity, again, I'm looking here. If t is very, very large, I'm going to get e to the negative infinity. And e to the negative infinity is 0. So that is going to cancel out and kill this entire term. And therefore, CA of t going to infinity is going to be equal to v dot over v dot over v plus k times CA0. All right, so I can plug in numbers and I can see what exact number value that is. But another way that I can double check is to solve for CA when dCA dt is equal to 0. Now, previously I said that you would set dCA dt equal to 0 when you want to find the maximum. However, this is a different type of problem. Or for the steady state solution, my accumulation term is 0. So if steady state, I can cancel this out and say dCA dt is equal to 0. All right, so that's what I'm going to do here. If I just simply solve this for dCA dt equal to 0, I'm going to come down here and erase that so that my notes aren't all messy later on. So 0 is equal to v dot over v CA0 minus v dot over v CA minus KCA. I think that was it. Let me just quickly double check. And yes, that is what it was. So now if I want to solve for CA, I can factor out the factor out the CA. So v dot over v CA0 minus, I'm going to do plus minus v dot over v minus k times CA. Take this term over to the other side. Minus v dot over v CA0 is equal to minus v over v dot minus k times CA. I've got a lot of negatives here, so I'm going to cancel them all. And finally, if I solve for CA, I get v over v dot CA0 over v dot over v, plus k. And let's see, this is my one solution. To be more precise here, I'm going to say CA at t tends towards infinity. All right, so notice, let's see, it looks a little bit different because I've left the CA naught in the numerator here. But these are the same value, which is good. So this is another indication that what I have done is correct. So that's another good way to double check what you've done. And just in case you want to double check yourself, if you wanted to plot this on Excel, this is what my plot looks like. I start at 2, and then it goes down kind of like this. My steady state value, so this is CA, this is T. CA steady state was equal to 1.92 moles per liter. So once again, this is a startup operation of a CSTR. Why this is useful in engineering analysis is I can now look at this curve and predict when my product is going to achieve steady state. So in other words, if I was making something, I would say, when is my concentration of CA close enough to my expected steady state value such that I can start taking product from this? That's an example of why this is useful in an engineering context. So that'll be it for this video. Thanks for watching. See you in the next video.